So we'll do chapter 13. Kinetic theory of gases. This is a theory, we're going to understand it. How then we going through its assumptions, we are going to then define pressure, find a relation of pressure based on this. When you put always before we carry on with this one, so throughout this chapter you will have to keep in mind, you have to always visualize and conceptualize that you have a closed cylinder. In this closed cylinder you have a given mass of a gas. You have a certain mass of gas, and we will see what kinetic theory of gases say. So in this chapter I am going to always be referring a gas which is contained in this cylinder, which is closed. Both these caps are closed, and we have a gas molecules here which are at constantly random motion. Very soon you will see they are so excited that they are moving in different direction. They are not only colliding with each other, but they are also colliding with the walls, and it is this collision that is called the pressure. We will see that how gas molecule exert pressure. So in the fluids we have seen the pressure related to, in the solids, in the mechanical properties of solid, we have seen how pressure plays a role. What is pressure we call is a stress and all. Then we came to see in fluids that how pressure acts in case of liquid, and in this case we will look into the another state of matter, that is called the gases, and how pressure and how pressure plays, how is pressure explained in case of gases. So with this in mind, let us start with the most basic laws, the most fundamental laws, that is without which it is not possible to understand kinetic theory of gases. The first law, which is called the Boyles law. So let us understand the most fundamental laws first, then we will try to derive these using kinetic theory of gases. Okay, so what is the Boyles law? Boyles law says that if you have this gas, if the temperature of this gas inside this cylinder is constant, then the volume of the given mass, according to Boyles law, the volume of a given mass of gas is inversely proportional to the pressure, to its pressure. As you have seen, the caps, they are imparting some pressure here on the top and down. So the volume of the gas will be indirectly proportional to the, that means in this case, so if this is a small container, let's say this is a very small container, this is of height h and this is of small height, this is the cap of the container. So in this case, definitely this volume, this is h dash and this is h, keeping their cross sectional area same, if I keep their cross sectional areas being same, the both being same, then what we can conclude is that the volume of the gas is now directly proportional to the pressure. So definitely pressure is large, so V is inversely proportional to P. So if P is large, V is less. Definitely, in this case, the pressure imparted by the caps of the cylinder in this case is large. So this is P1. Definitely, this is P2. This is P2. So you can see this is P2. So clearly P1 is greater than P2. So definitely V1 is less than V2. This is what. But yes, you have to keep the temperature constant. In both the cases, T equals to constant. This is what it is saying. That means if you have a, indirectly in one simple way you can understand Boyle's law says that if you have a long jar, if you have a big jar, you will be the same same group of molecules will take a greater volume. If you have a small jar, then it will take less volume. So now this is how you can remember Boyle's law looking at this picture. So clearly we can say that, so if I remove this, PV is equal to, we can write this, PV equal to some constant. So looking into these two equations, we can say, so P1 and V1, let's say they are the initial volumes, are the initial volume in this container, initial pressure and volume, and P2 and V2 are their final volumes and pressure. Then we can say P1 V1 equal to P2 V2. This is what I have written here, right? And the ratio is P1 by P2 is equal to V2 by P1, V2 by V1. Correct? So if you plot a curve, if you see the arrangement properly, if you look at the curve, you will see definitely pressure and volume, they are inversely proportional. Let's say this is the volume, this is the pressure, they are inversely proportional. As you can see, they are inversely proportional. So we can draw, the graph will be a rectangular hyperbola. This is the equation, this is the graph of rational functions as well. So it is something like this. The two arrows represent that they are going towards infinity. So T equals to here is constant. Secondly, if we see now, so if we pay attention to this one, this equation, here K can be our T or whatever. So if we look at this equation, PV is equals to K, that means we can write P is proportional to 1 by V. So if we try to plot a curve in this case, so let's say this is P, this is 1 by V. You can see it's a directly proportional curve. So they vary linearly. We can use this curve more properly to compare two gases. Compare the volume and pressure of two gases. Okay. So maybe some other, I guess, which one P by V, if I do which one. For example, if I give you one question here, what I mean to say, let's say an example. I give you the equation of two gases. This is the P versus 1 by V graph, and these are the two. This is one gas A, this is another one, this is B. So which gas A or gas B is at higher pressure? Definitely you can see, we can say that A is at large because directly proportional, B is at lower pressure. That means if this is large, that means its volume is less. So V is in much more compressed state and A is much more in the relaxed state. So this is how. So let us come to the next law. Next fundamental law is called the Charles law. So if you look at this thing, look at this first picture, a gas in a container will have three main important properties. What are the different physical properties, the physical quantities involved? First thing is pressure is involved, volume is involved. It has volume, it has pressure, it also has some temperature. It has some temperature. It has some mass. We'll come to that. It has number of molecules. Number of molecules. These are different things that is present there. So all the gas laws is somehow will be around this thing. So next thing is the Charles law. So Charles law says that this law gives the relationship between volume and temperature, V and T, keeping P constant. So now let's say if the pressure is constant, so again let us look into that cylinder. We keep the cylinder here. There is some container which is enclosed with some gas. A constant mass of gas is present there. This is the cap which is closed. Here we have the gas molecules. Which are moving randomly in all possible direction. They're colliding with each other, colliding with the walls and so on. Now what do we do? If we increase the temperature, what will happen to the volume? Is it going to increase or decrease? If we increase let us see what this law has to say. Now we are not going to, if the pressure is now constant, we are not making the container caps very tight, or we are not decreasing or increasing the volume of the cylinder. We are keeping it fixed. So pressure remains. So P equals to constant in this case. It is not changing. So it is not putting much of pressure from the top or bottom. Now it is fixed. But what are you going to do? We are increasing. Maybe we are heating it. We are using some kind of thing to heat it. Okay? So then what do you expect will happen? If we're giving some heat, is the volume increases or decreases? So Charles law, according to Charles law, if the pressure remains constant, if the pressure remains constant, then the volume of a given mass of a gas increases or decreases by 1/273.15. There's a point here, 273.15 of its volume at 0 degrees centigrade. So we need to have a reference. Imagine at 0 degrees centigrade what was its volume, at 0 degree centigrade, if I draw this same container once again, this is at 0 degree centigrade, the volume of this gas will be very small. It will be the gas will be in a very less volume. So this is our reference. So maybe the molecules will be restricted within this portion. Rest of the thing is empty. This is empty here. At 0 degree centigrade. So the volume of the gas within this container is fixed within this little region, little volume. So for now you understand like this. So therefore, volume at 0 degree centigrade. So what I was saying, according to Charles' law, if the pressure remains constant, then the volume of a given mass of gas increases or decreases by 1 by 273.15 of its volume at 0 degree centigrade by volume of for each 1 degree centigrade rise, 1 degree centigrade rise or fall of temperature. It means the new volume will be, for every 1 degree rise, it would be 1 by 273 times the volume it had in 0 degree centigrade. Mathematically we can write, let V0 is the volume of the given gas. So this is our V0. This is my V0. This is the volume of the gas at 0 degree centigrade, and Vt is the volume of the gas at any temperature, with the volume of the gas and any temperature. Or let's say like this. Let's say before we go, let's say this is initial volume. So V1 or V2. So volume of the gas at, let's say, 1 degree centigrade. At 1 degree centigrade, it would be initial volume plus 1 by 273.15 times the volume at 0 degree centigrade. At 0 degree centigrade. So we can simplify a little bit further and write. So V1 can be written as V0 and then 1 plus 1 by 273.15. Similarly, if at 2 degree centigrade, at 2 degree centigrade, what does we mean? It will be 2 at V2 degree centigrade will means V0 plus 1 plus 2 by 273.15. Similarly, at 3 degree centigrade. So similar at 3 degree centigrade, we can write like this. V0 would be 1 plus 3 by 273.15. So therefore we can generalize it. So volume at T degree centigrade would be Vt will give me then V0 1 plus T by 273.15. This is how the volume of the gas. So we can see volume of the gas depends on temperature, keeping the pressure constant. So remember, you have a gas cylinder at home which is in the liquid state, but there is gas also there. So we will talk about this after we go through all these laws. What is going on? Think about it. With all these gas laws, how they are playing there, think about it a little bit. I'm giving you a hint, giving you the first thing to brainstorm your mind, how these laws are applicable there. Again, moving forward, so let us see what other variations we can do. So let T0 and T are temperature of the gas at 0 degree centigrade and T degree centigrade in Kelvin scale. Then we can write, so T0 can be written as 273.15 plus 0. That gives me 273.15 Kelvin. So T will be again 273.15 plus T. This is in the Kelvin scale. Therefore, our relation will become now, if we take, so Vt and V0. So Vt by V0 can be written as, so Vt by V0. Look at this equation, this one and the V0 one. If I take this, bring this here, 1 plus T, so T is 273. So we can write this as 273 plus T. So this one, let me write a little bit. So capital T. So then T comes out to be, so 1 plus this T can be written as 273, capital T minus 273.15 by 273.15. On simplification, we see that we can write this 273.15 plus T minus 273.15 divided by 273.15. So these things get cancelled, so we're left with T, and what is this? This is T0, T by T0, T by T0. So Vt by V0, we see that they are like this. So I'm so badly written, let me write it properly. So we can see that Vt by V0 is equal to T by T0. So what can we conclude? What conclusion can we draw from here? We can conclude that. So look at this picture and see. So we are different temperature we are seeing. This is at temperature T, this is at 0 degree centigrade. So at 0 degree centigrade at temperature T, we can see the volume is directly proportional to temperature. You increase the temperature, the volume also increases. So imagine you keep increasing the volume, you keep increasing the volume, you keep heating this one. As it gets more and more heated, the volume is increasing. As its volume increases, keeping the pressure constant, now what will happen? It will try to burst out. It will try to blast. Okay? So then we can conclude that V by T is equals to constant, or V is directly proportional to temperature. Again, we can have a curve. The curve states that so keeping the volume and temperature V, this is T in Kelvin. We see the line is a straight line. Is a straight line. So V by T is a straight line. What was the V by P versus V curve? P versus P curve is a rational function, inversely proportional curve. But P versus 1 by V is a straight line. Similarly, in here, V versus T is straight line. Okay? So these are the two laws we have seen. Now let us come to another fundamental law. The next important law. That is the next fundamental law. Lussacs law. So first one, Boyles law, dealt with pressure and volume. Second one dealt with volume and temperature. So this one must be between pressure and temperature. Okay? So this states that, so what do you think? Again, we will have a look at this. We'll look at this cylinder now. We need to visualize that this cylinder contains or gas If we now keep the temperature constant and vary with the pressure, if we keep the volume constant, if we keep the volume, this volume constant, and play with the temperature, that means we keep heating it, how does the pressure increases or decreases? That is we need to see now. Okay, how does pressure vary? Pressure will increase or decrease. So this is the molecules which are always in random motion in all possible direction. They are not only colliding with each other, but they are also colliding with the walls, surface, everywhere. They are colliding with the top surface as well. Everywhere they are going like this. So Gay-Lussacs law states, according to this law, the pressure, keeping the volume constant, the pressure of a given mass of gas, increases or decreases, or decreases by 1 by 273.15 times 1 by 273.15 of its pressure times its pressure, 1 by 273.15 pressure at 0 degree centigrade for each 1 degree centigrade rise, for each 1 degree increase or decrease in temperature, for 1 degree increase or decrease in temperature. Okay, so same way, if I am heating this one, keeping the volume constant, if I am heating this, got it? So if you are heating this, so if you are keeping the volume constant, keeping V constant, so pressure will increase or decrease. Same way we can prove that. So P T would be P0 1 plus T by 273.15. Same way it can be proved. How I have proved earlier, like this way, how I have proved here. Same way it can be proved that P1, so PT by P0 will give me T by T0. So again here we conclude that pressure is directly proportional to temperature. So the curve, I'll draw it here. This place is empty. So let me draw it here. Again the curve will be straight line. Means you increase the temperature, the probability of that gas inside the cylinder of trying to, is very strong force. They will try to blast, they try to break the cylinder is more. So in a cylinder, if you have a gas cylinder at home, it is advisable to keep it in a place where it is cool. Surrounding temperature should be less. So in the normal room temperature, 25 degrees centigrade, the container vessel is so strong that it can build it. But when there is a fire break out in a household, you will see the cylinders blast. Why? The surrounding temperature increases rapidly. They are in a very high degree centigrade, and as it is a very high temperature, the gas inside the The gas cylinders, their volume, they are trying to increase the volume. As a result, it blasts. And it blasts, and they are very much feasible. They are very much ignite. They ignite, and then you can see the catastrophe. So this is how pressure and volume, they are directly proportional. So we see P, pressure and temperature. This is how the slope will give you. Let us see what that does give it. So these are the three fundamental laws, gas laws. First is the Boyles law, which talks about keeping the pressure constant. We talk about keeping the temperature constant. It talks about volume and P. Second law talks about the Charles law. This gives you the relationship between the volume and the temperature, keeping the pressure constant. And the Gay-Lussacs law gives you the relationship between the pressure and the temperature, the last PT. So knowing all this, we can come to something called, so if you know all this, what we can do with this? So from the gas law, from the three fundamental gas laws, we see that, so from Boyle's law, we see that V is proportional to P, and this is Boyle's law. Then we see V is proportional to T from Charles' law, and from Gay-Lussacs law we see that pressure is proportional to temperature. This is Gay-Lussacs law. So if we combine all of them, combining the three laws, what do we see? That V is proportional to T, V is proportional to, okay, we can remove this, we can use this, we can combine it and say that V is proportional to T and V is inversely proportional to P. Or we can write V equals to constant into T by P. Or we can write this, we get constant by key. Let's say P equals to V equals this. So now how much amount of gas is present? So let's say, there is 1 mole of gas. For 1 mole of gas, remember mole is the SI unit of quantity, matter. For 1 mole, which is very basic, 1 mole of gas, the constant, I can name this as A, B, whatever, the constant is same for all the gases. Hence it is called universal gas constant. Hence it is called universal gas constant, denoted by R. So R is, so that means V equals to R into T by P. So we can write this, PV is equal to RT. This relation is called ideal gas equation. This relation is called perfect. This relation is called ideal or perfect gas equation. Remember, for N equals, for only 1 mole of gas. For N mole, let us see for N mole, what is it? For N moles, so 1 mole is that much. So for N mole, we should multiply it. So for N moles, PV would be equals to nRT. For n moles, P equals to nR. This is also perfect or ideal gas equation. Ideal gas equation. Okay. Now if V is the volume, let's say V is the volume of 1 gram mass of gas. We need to know what is R. Let's see what is R and how we can do with that NR. 1 gram mass of gas, and M0, let's say M0 be the molecular mass of the gas, then how can we write? N can be written as mass of the gas in gram divided by molecular mass. So for 1 mole, for 1 gram, V is the volume of 1 gram mass, so that means this will be 1. So N will be 1 by molecular mass, right? Therefore P, this is not capital V, small v can be written as PV equal to, I am writing in a different way to highlight you, 1 by M0 RT. This is the same perfect gas equation in terms of, so we'll denote this R by M now. So P small v will be equal to small r into T. This is for 1 gram. This is in terms of gram. When you are dealing with the gram mass, 1 gram of mass, 1 gram of gas, then this is the equation to follow. This is perfect gas equation. This is the perfect gas equation for 1 gram of gas. Here R is equal to R by M0. Okay, then let us come to another, a very important fundamental constant, Boltzmann constant. So this is a very important constant, will be Kb, denoted by Kb. Kb is equal to universal gas constant per molecules. So it is universal gas constant by Avogadro's number, Avogadro's number. Therefore R is equal to Kb in A. So number of moles N can also be written as, think about it a little bit. So how do you define? Mass of the gas by molecular mass. So we can define N as, in terms of number, as number of molecules by Avogadro's number. I hope you know that it is Na is called the Avogadro's number. Avogadro's number. This is a certain number of molecule this is a constant number. You know this in chemistry. So if I go, I'm not going into that much now. So if we use this here, so that means our relations comes out to be N by Na, right? Therefore, PV is equal to nRT. So in terms of Boltzmann constant, I can write N as N by Na and R as, in terms of Kb into Na into T. So this get out. So in terms of Boltzmann constant and number of molecules, perfect gas equation can also be written as Kb into Nt. This is the perfect gas equation, ideal gas equation in terms of the Boltzmann constant. Boltzmann constant is one of the fundamental value. We will find its value. Let us find out, let us calculate now the universal gas constant's value and also the value of K. So R equals to, we see, value of R and K and Kb. So we know R is equal to PV by N into T. Okay. So P is pressure, volume. So pressure can be written as pressure into volume. So we can write this as, so pressure is force by area and volume is area into cross section length. So pressure into volume would be work done. Therefore we can write this as W by number of molecules, number of moles into temperature. So clearly the gas constant is work done. Gas constant is work done per unit moles per unit mole per unit moles per Kelvin. Because this is in Kelvin. You can see from here we have taken this in Kelvin. I've taken this in Kelvin. T is in Kelvin. So per Kelvin. So SI unit of R will be, work done is joule per mole per Kelvin. So SI unit of R is this. At standard pressure, at STP, so at STP, standard temperature pressure, at STP, P is equal to, we know, 0.76 760 millimeter of mercury, 760 millimeter of Hg, which we can write this as 0.76 meter of mercury. Temperature, that 0 degree, would be 273.15 Kelvin. If we use the volume of the gas would be 22.4 liter. You must know this. At standard temperature pressure, the volume of 1 mole of gas, and N equals to 1 mole. So the volume of, as STP, the volume of 1 mole of gas would be 22.4 liter. And 22.4 liter means that 1 liter is 10 to the power minus 3 per meter cube. Meter cube, not per meter cube, meter cube. So it should be 22.4 into 10 to the power minus 3 meter cube. So we use this data here. R will be equal to PV. P is millimeter of mercury. So pressure, we need to convert it into mercury. Remember Hg of mercury. So you know this, how to do this one. It is this value here, P equals to rho GH. That would be the pressure. So pressure can be written as rho G. G is for Hg mercury into H into this volume would be 22.4 into 10 to the power minus 3 divided by N is 1 mole into 273.15. So that gives me rho is density. What I am writing this? So sad, so bad. This would be density of mercury. This is Hg. This is G. This is H. This H is 707.067 and mercury density is 13.6 into 10 to the power 3 into 9.8 into 0.76 into 22.4 into 10 to the power 3 divided by 273.15. So if I solve this, I'm going to get this value to be 8.31. And what is this unit? Joule per mole Kelvin. So joule per mole per Kelvin. This is R. This is the value of R. Now we can use this relation. We can use this relation to find the value of K. So Kb is equal to R by Avogadro's number. You see here we have done just few minutes back. Kb is equal to R by Na. Therefore R is 8.31 divided by Avogadro's number 6.02 into 10 to the power 23. 6.02 into 10 to the power 23 per mole. And this is joule per mole per Kelvin. So we get this here, per mole get cancelled. This value comes out to be 1.38 into 10 to the power minus 23. Minus 23 joule per Kelvin. This is the value of Boltzmann constant. We will be frequently using this in this chapter.